Hi, in today's video, I'll be going through the basic concepts of CUDA programming and talk about what are kernels, grids, blocks, threads, and warps. So the contents of this video will first cover memory and what exactly is the device in the host. We'll talk about what exactly is a kernel function and how do we instantiate that. We'll also go through streaming multiprocessors, grids, blocks, threads, and warps. And lastly, we'll have a coding example where we use CUDA to double elements in an array. So before we continue, I wanted to introduce two high-quality resources. So one is the NVIDIA CUDA C++ programming guide, which you can access by scanning the QR code below. And the other is a textbook, Programming Massively Parallel Processors by David Blair-Kirk and Wan Mei. So let's talk a bit about the GPU and the CPU. So in CUDA programming, we typically refer to the host as the CPU and its memory, and we refer to the device as the GPU and its memory. So both the CPU and GPU have its role to play in processing algorithms. So the CPU excels more at sequences of operations. So for example, the CPU is able to do speculative branch prediction. However, the GPU excels more at executing many operations in parallel. So where the logic is not too complicated, but there's a lot more operations, this is where the GPU excels in. So as you can see in the diagram below, the GPU has many more transistors for data processing. So going more to the CUDA side of things, so we first learn what is a kernel, where a kernel is a function that is executed on the GPU. And this kernel function can be instantiated by adding the __ global _ identifier beside your usual function definition. So next we talk about streaming multiprocessors. So streaming multiprocessors are the execution unit of the GPU, and what they actually execute are warps, which are a group of 32 threads. So in CUDA, threads are organized in terms of grids and blocks, where a grid is a collection of blocks where the max number of blocks is dependent on the device. So for example, in 34 GPU, you can have up to 9 quintillion blocks, which also explains why GPUs are so good at processing many operations in parallel. Next, we also have the block, which are a group of threads that are executed on the GPU. And a thread is basically the smallest unit of execution in CUDA, where each thread executes the same code but operates on different data. So here is the hardware diagram for the streaming multiprocessor. We see that it has memory units such as the register file and the shared memory. And it also has CUDA cores, which is what will execute the warp, as well as the warp schedulers, which does the scheduling of the warps. So to recap on what a warp is a set of 32 threads such that all threads in a warp execute the same instruction. Furthermore, all threads in the warp are guaranteed to be synchronized. So what this means is that if a few threads have finished executing while some of the threads are still not done, the warp will have to wait for all the threads to finish executing before it can complete. And lastly, one CUDA warp can only be processed by one CUDA core in the streaming processor only. So let's talk about a process where a programmer has already defined a kernel function and now he wants to call this kernel to run on the GPU. So first he has to specify certain attributes such as the grid dimension and the block dimension. So what exactly is the grid dimension? So the grid dimension is the number of blocks in each X, Y, and Z axis, while the block dimension is the number of threads in each X, Y, and Z axis. So we also introduced two new concepts, which is the block index and the thread index. So given a specific block or a specific thread, the block index specifies the current index of that particular block, while the thread index specifies the X, Y, and Z portion of that particular thread. So for example, in the visualization, we can see that the grid dimension is a 3 by 3 by 3, where there's 3 blocks in the X dimension, 3 blocks in the Y dimension, and 3 blocks in the Z dimension. We also see that the block dimension in terms of the number of threads is 4 in the X dimension, 1 in the Y dimension, and 4 in the Z dimension. So to get the block index of the purple block, we can see that its X coordinate is 0, Y is 0, and Z is 2. While for the yellow thread, it is 0 in the X, 0 in the Y, and 3 in the Z. So once we have specified the number of blocks and the grid dimension, the GPU will start to assign these blocks to each streaming multiprocessor. However, the streaming multiprocessor do not process these blocks directly. They have to first partition the blocks into warps, and each of these warps contain 32 threads. So here we can see why it's preferable to specify the block dimension in multiples of 32 so that it is able to more efficiently partition them into the warps. So now that we have covered concepts such as the streaming multiprocessor, blocks, and grids, but we also understand that different GPUs have different specification. So one way of attaining this specification is to go online and check the technical documentation, but we can also retrieve some of these attributes through software. So for example, in this instance, we are instantiating a CUDA device prop, and from there we can extract many properties such as the maximum number of threads per block, the maximum thread dimension, the grid size, and also the multiprocessor count. So another thing about CUDA programming is that memory is not shared between the host and the device. So in order to run algorithms on the GPU, we need to find ways to first transfer data from the host to the device to run workloads. So the first thing that we learn is we can use a CUDA malloc to allocate memory on the GPU. So as you can see in the diagram, we have allocated some memory in the GPU. And in order to transfer from the host to the device, we can use a CUDA memcopy and specify a CUDA memcopy kind of CUDA memcopy host to device to copy data from the host to the device. Secondly, we can also do the reverse operation. So this is a two-way thing where we can do a CUDA memcopy from the device to the host to copy data from the GPU to the CPU. Lastly, after we're done with the processing, we want to be able to free the GPU memory by calling CUDA free. So let's run through an example where we want to double elements in an array. So suppose that we have an array of 1, 2, 3, 4, 5 in the CPU memory at the moment. So how do we run a CUDA operation on the GPU? So the first thing that we have to do is to allocate memory in the GPU using what we have learned before, using CUDA malloc. Once we have allocated memory in the GPU, we can then send the array from CPU memory to GPU memory using CUDA memcopy. After we have done that, and the data resides in the GPU, we can now call the kernel function to double each element in the array. So for example, in this case, the array is now 2, 4, 6, 8, 10, and all the elements have been doubled. However, this change is only being reflected in the GPU, and we are still unable to access it from the CPU. So we need to do another CUDA memcopy to send the array from the GPU memory to the CPU memory. And lastly, once we have done all these operations, we want to free the GPU memory using CUDA free. So now we'll go through a coding run through where we'll double elements in an array using CUDA. So now we'll switch over to Colab. So in order to reduce the number of setup that you do, we use Colab so that we can immediately start getting some CUDA code running. So the first thing that we need to do is to ensure that our runtime is using a GPU. So in this case, it's using the T4 GPU. And what we need to do is actually do some setup where we install MVCC for Jupyter, and then we run this, and then we have to load the extension. So we call load extension MVCC for Jupyter, and just with these two lines of code, we should be able to get up and running with CUDA code. So one thing that we have to do is we'll start off with a demonstration of how we can get the device properties as shown in the slides. So let's call this get device props.cpp, and we will instantiate a main function, and now what we want to do is to actually get the device property. So we'll call this the device prop, and then the first thing we'll call is CUDA get device. So we will get the device, and then we also want to get the device property, so we can pass in the device prop as well as the device ID. So to run this, we actually need to include, so we need to include CUDA runtime.h, and to print we shall include IO stream. So let's start out by printing out the name of our device. So now that we have gotten the device properties, we can print the device property name. Let's add some text for more clarity. So call this device name. And now that we have this, we should be good to go. So to run the code, we need to compile it. So let's use a shell script, and then we will compile it with MVCC. So we will call this get device props, and then we will compile the CPP file. Okay, and then we will call get device props. So now that we run, we see that we are able to get the device name. However, we can also get other attributes such as the max thread block number of threads per block. So this could be device prop dot max threads per block. And we can also see how many streaming multiprocessors there are. So streaming multiprocessors, and this will be the device prop dot num multiprocessor count. And if we were to run this, we will see that we are able to get the specifications of our device. So here we can see that the T4 actually has 40 streaming multiprocessors. So the next thing we want to do, now that we have learned how to compile code and run on Colab, is we want to specify our CUDA program to double elements in array. So we can call this double array.cu. So this is the file extension for CUDA programs. And then we can first specify our kernel. So kernel, and I'll call this double array kernel. So this is our GPU function. And what you do is take in the pointer to the array as well as the size. And then we will implement this later. So I'll first put a return. And then now we will specify the array function. So this takes in array again and size. Okay, so we will implement this soon. So now we can write this file. So another thing we want to do is to do a CPU implementation first so that we can compare the outputs. So let's just call this main.cpp. So we can specify a main function. Okay, so first we can define a size for our array. So let's say I decide to use a size of 50. And now what we want to do is instantiate an array. So let's say I have a insta CPU array, and then we call this new in size. Okay, now that we have specified the array, we want to initialize some value. So for in I equals 0, I less than size, and I plus plus, we will then initialize the array. And what we want to do is, so to print, we need to include IO stream and print the original array values. So print original array, and then we will print the original array values. So we will print the original array values, and then we do comma. Yeah, so we will close up. Okay, so now we want to do a CPU implementation. So for example, I were to do cout, and I'll call this CPU implementation, and then I will double all elements in the array using the CPU. So let's do the loop again, and then we take the array and then we double it, and then now we want to print out the value in the CPU array. Yeah, so let's add a new line here so that it will print nicely. And then now what we'll do is we want to print out the values. So now that we've written a main, we can do the same thing. We can compile it. So let's call it shell, and then we specify fvcc-o main.cpp, and then so let's run this. Okay, I think I may have missed out a few semicolons. And now we see that it is able to double the elements in the array itself. So this is good. That means our CPU implementation is working. But now we want to run the CUDA code to double the array. So how do we do that? So first, let's specify our kernel function. So the first thing we want to do with our kernel function is to get the index. So the in index will be equals to the current block dimension times the block index, and then we plus the thread index. So this will give us the index of the thread. And because when we're running kernel functions, we're running in terms of the blocks themselves, so the block size might be greater than the array itself. So for example, if my array is only 50 elements but my block size might be 128, so that means all the threads above 50 are still going to run. So what we want to do is we need to make sure that only if the index is below than the size, then we will perform the computation where we take the array and then we double it. Yep, sorry, so this index. So now we're done with our kernel function. So now we actually need to do the process like we showed in the slides to transfer memory from the host to the device, do the computation, and then transfer back from the device to the host. So how do we do that? So first, we want to do a CUDA malloc for the device array. So we do CUDA malloc device array, and then we specify the size, which is size times the size of int. So now that we have done the CUDA malloc, we can then copy from the host to the device. So CUDA mem copy, the destination, the source is from the array. We again do the size of int, and then we will specify CUDA mem copy host to device, and later we'll want to copy the array back. So now I will specify it here, and here we shall change it to device to host. Okay, so now inside here we can finally call our kernel function. So first thing we want to specify is the threads per block. So we can specify, let's say 128, and so now we have to calculate the number of blocks that we need. So in num blocks, so to ensure that we have at least one block, we will take the current size plus threads per block minus 1, and then we will divide it by threads per block. Okay, So now we can call our kernel function, which is the double array kernel. And what we want to do is specify the number of blocks and also the threads per block. And then we can call the function with the array as well as the size. And then once we have copied it back, we should free the GPU memory. So CUDA free the array. So now we're done. So now we want to run the CUDA code in our main function. So how do we do that? We can specify a header file. So let's do write file CUDA functions.h, and then we can specify if it's not defined already, then we define CUDA functions h, and then we specify the double array with pointer to the array as well as the size. And then so now that we have defined this, we can finally run our CUDA function. So let's include CUDA, the header file, and let's specify one for the CUDA. So let's just call this the CUDA array, and then again let's initialize so we can compare the CUDA and the CPU version. So CUDA array, then we initialize it, and now we can do the CUDA implementation. So let's first call our double array, and then we pass in the CUDA array as well as the size. So we are calling our CUDA function, and then now we want to print it. So let me just take this, and then I'll call it the CUDA implementation. So we don't need to double it, and we just take the CUDA array. Okay, so we should be done, and now we can run it and see if we get the correct output. Okay, so we got a undefined. Let's call this double array CUDA. Just for clarity, and then alright, because we need to compile it. So remember to compile your files. So double array .CUDA. Okay, let's see if it works. Yeah, so good job. We have managed to implement a CUDA function to double array. Yeah, that's all for today's lecture. Thanks for joining, and yeah, hope we can continue to learn more about CUDA together.